Good morning, champs. Today we are going to extend the centroid method from the previous example to an area containing a curved boundary. The important thing is that we are not introducing a completely new idea. We are still calculating an area weighted average. The difference is that one part of our geometry can no longer be divided conveniently into simple rectangles and triangles. Our plate begins as a square that is 4 meters wide and 4 meters high. Inside the square, we have the parabola y equals x squared divided by 4. It begins at the lower left corner and reaches the upper right corner. The area underneath this parabola is removed. Our goal is to determine the centroid of the material that remains above the curve. We can think of the problem as a composite area. We have the complete rectangle, and from it we subtract the curved area underneath the parabola. Before we can use our composite area formula, however, we need to determine the area and centroid of that curved region. In the previous video, we calculated the centroid using a sum of individual areas. We multiplied each area by the position of its centroid, added those contributions, and divided by the total area. For a curved region, we can imagine dividing the area into a very large number of extremely thin strips. As the strips become infinitely thin, each small area becomes a differential area dA. Our sum then becomes an integral. So the horizontal centroid is obtained by integrating x times dA and dividing by the total area. The vertical centroid follows exactly the same idea. This is important. Integration does not change what a centroid means. It simply allows us to apply the same area weighted average idea to a continuous shape. For our parabola, vertical strips are particularly convenient. Consider one very thin vertical strip at position x. Its width is dx, and its height is given by the parabola, which is x squared divided by 4. Therefore, the small area dA is x squared divided by 4 times dx. Before integrating, we also need to know where the centroid of this tiny strip is located. Horizontally, it is simply at position x. Vertically, the strip behaves like a very thin rectangle. Its centroid therefore lies halfway up its height. Since the full height is x squared divided by 4, the vertical coordinate of the strip centroid is x squared divided by 8. We can now calculate the area underneath the parabola. We integrate x squared divided by 4 from 0 to 4. This gives 16/3 square meters. Next, we determine the horizontal centroid of this curved area. We integrate x times dA and divide by the curved area. Performing the integration gives a horizontal coordinate of 3 meters. For the vertical coordinate, we multiply each differential area by the vertical position of its own centroid. The strip centroid lies at x squared divided by 8, while the differential area is x squared divided by 4 times dx. Integrating their product from 0 to 4 and dividing by the total curved area gives a vertical coordinate of 1.2 meters. So the centroid of the curved region underneath the parabola is located at 3 meters horizontally and 1.2 meters vertically. Now we return to our original composite plate. The complete rectangle has an area of 16 square meters, and its centroid is located at 2 meters horizontally and 2 meters vertically. The curved region has an area of 16/3 square meters and a centroid at 3 meters and 1.2 meters. But there is one very important difference from our previous composite area example. This curved region is not material that we are adding. It is material that has been removed. For centroid calculations, we can handle a hole or cutout simply by treating its area as negative. So the rectangle has a positive area of 16 square meters, while the curved cutout has a negative area of 16/3 square meters. The remaining area is therefore 16 minus 16/3, giving 32/3 square meters. Now we can use exactly the same composite area formulas as before. For the horizontal centroid, we take 16 times 2 minus 16/3 times 3 and divide by 32/3. This gives 1.5 meters. For the vertical centroid, we take 16 times 2 minus 16 thirds times 1.2, and again divide by 32 thirds. This gives 2.4 meters. Therefore, the centroid of the remaining plate is located 1.5 meters from the left edge and 2.4 meters above the bottom edge. Before finishing, we should check whether this result makes physical sense. The centroid of the original square was exactly at 2 meters and 2 meters. We removed material primarily from the lower right portion of the square. Removing material from the right should shift the centroid toward the left, and removing material from the lower part should shift the centroid upward. Our calculated centroid moved from 2 meters to 1.5 meters horizontally, and from 2 meters to 2.4 meters vertically. So the result behaves exactly as we would expect. The key lesson from this example is that the integral centroid formula is not a different concept from the composite area formula. With a few simple shapes, we use a sum. With a continuously varying shape, we divide the area into infinitely small pieces and use an integral. And when part of a composite area is removed, we simply treat that part as a negative area. This gives us a powerful method that we can now use for much more complicated centroid problems.